Today we're talking about memory, and not like the brain, but in the Game Boy. How are programs stored? How does the processor remember things? Where does memory fit into the Game Boy's execution model? We're going to answer these questions, somewhat. But first, just so you all know, we're going to make a Game Boy emulator and learn Rust and WebAssembly in the process. You should go watch the first intro video if you haven't. There's a link here. And you should sub and thumbs up and follow me on Twitter and GitHub and all the places. Okay, remember the goal from the beginning. Wait for it, wait for it, wait for it. So we want to get this thing to work. To do so, we really need to understand how the Game Boy works. Let's start off by picking one specific Game Boy. We're going to study the original Game Boy Pocket, which had a DMG-01 processor in it. Right when you turn on the Game Boy screen, this processor starts doing stuff. And that stuff was figured out by this person named Naviksty in 2003. Naviksty decapped the processor and read the bits out using a microscope for the code that executes when the Game Boy first turns on. This code, by the way, is called the boot ROM. Naviksty figured out what these ones and zeros meant by converting the data into code. There's this notion that code is data. What do I mean by that? The instructions, for example, LD, SB, $FFFE, XOR A, LDHL, 9FFF, corresponds to the bit string 00110001111111, etc., and vice versa. These zeros and ones are kind of hard to deal with. It's kind of like looking at ants walking around. We tend to use something called hex or hexadecimal, which compresses the binary data into a more readable form. For example, this binary string corresponds to the hexadecimal 31 FEFF-AF. By convention, we prefix hexadecimal numbers with either a $sign or a 0x. A single byte is represented by two hexadecimal glyphs. Each hexadecimal glyph varies over 16 values, and 16 times 16 is 256. Examples are AF, A3, 4C, and 30. If you want to learn more, you should go check out the Wikipedia page on hexadecimal numbers. These instructions are part of the ROM, or read-only memory, on the Game Boy. For the viewer's pleasure, I now show the assembly code corresponding to the binary code that was originally discovered back in 2003. And here are those instructions in hex. Y'all should check out hexdump, it's pretty cool. And of course, there's Rust. The boot ROM is a constant 256 bytes, or 0x100 in hex, and so we can declare a pub const boot ROM, which is of the type an array that is exactly 256 elements long. With some Vim macros, we can type out the hex dump. And that's what this is. The boot ROM is located inside the Game Boy device itself, but there's another type of ROM that's located on the outside, and that is inside Game Boy cartridges. Inside the Pokemon Blue cartridge, it'll look something like this, and one of these microprocessors is going to be a ROM chip, and it connects to little pins, and those pins connect to different parts of the Game Boy. However, we're just going to focus on the boot ROM at first, so we're not going to spend too much time thinking about this yet. There's also RAM, or random access memory. RAM, in addition to being writable, is also volatile. This means when the Game Boy turns off, the data is essentially lost. The Game Boy has a few different types of RAM. There's 8 kilobytes of static RAM, or SRAM. On your laptop, SRAM is the type of thing that's in your CPU cache, not in the part of the laptop that you normally refer to as RAM. That is DRAM, or dynamic RAM. The first 8 kilobytes is the general purpose RAM, but there's also another 8 kilobytes that's designated for video RAM. This is a surprisingly small amount of video memory. 144 times 160 pixels is a much bigger number than 8 kilobytes. The Game Boy does some crazy things with video, and we'll definitely explore that in a later episode. Typically, when people refer to fast RAM, they mean static RAM and not dynamic RAM. But there's actually some memory on the Game Boy that's way faster than SRAM. Registers let us read and write a really tiny amount of memory really quickly. The Game Boy has 6 2-byte or 16-bit registers, AF, BC, DE, HL. These are general purpose registers. In some of these registers, you can treat half of it as a single 8-bit register instead. SP is the stack pointer, and PC is the program counter. We'll spend more time on SP and PC in a different episode. The top half of the AF register is specifically allocated to flags. The flags are ZNHC. It stands for 0, add or subtraction, half carry. We will use these flags when we deal with arithmetic instructions, but for now we'll ignore them. Of course, registers can hold arbitrary data, but sometimes we can interpret that data as an address. In the Game Boy, addresses or pointers are 16 bits, 2 bytes, can span 65,536 values. For example, $A0C3 is one such pointer. Let's dig into the Rust representation of the registers. At first, we'll open registerkind.rs. Here we can see two enums, registerkind 8 and registerkind 16. In registerkind 8, we have A, B, C, D, E, H, L, as these are the 8-bit addressable registers. We derive debug, clone, and copy. Debug lets us print it out. The clone trait means that you can explicitly clone a value to make a copy, and the copy trait means that you can implicitly clone it. This also means we can avoid Rust's move behavior for these values. This is the type of thing that you want to do on very simple types. We also have an enum here for register kind 16, which is BC, DE, HL, and SP. The flags we're going to treat separately, so AF is not here, and the program counter we're also going to treat separately. In register.rs, we have at the top two new types, R16 and R8. R16 just wraps a U16, and R8 just wraps a U8. This pattern lets us have a little bit of extra type safety. Whenever we mean to refer to as the value inside of a register, we use an R8 rather than a U8, and that way we can't get ourselves mixed up with U8s that are used in other places. These also derive partial eq. Partial eq is equality without the reflexive relation. This is so that we can use partial eq on floating point numbers, because not a number does not equal not a number. It's a weaker notion than eq. Here are a few operations we have on a 16-bit register. We can get the high bits out, and that only needs a read-only copy. We can also do the same thing with the low bits. This just uses some bit masks and shifting. We can also increment if we have a mutable reference, and we can decrement if we have a mutable reference. In Rust, addition and subtraction using the operators panic in debug mode if you overflow or underflow, so we can use wrapping add or wrapping sub to avoid that behavior. On 8-bit registers, we can concatenate a high with a low using shifts in bitwise OR, and we can also increment and decrement in the same way. In Rust, it's cool. You can use those other implementations to help define your later ones. So here we have set high and set low, which extracts the other side, either high or low, and takes the new value and then plugs it in the right spot with concat. Now this is really cool. In Rust, you can inline your tests in the same file. If you just stick this config test attribute above a module, inside this test module, we're using prop test, which is a crate that gives us quick check-like functionality. Quick check style testing frameworks let us state properties. For example, that a 16-bit register can be decomposed and recomposed. This is a good way to test correctness of your functions. Then we can write down the flags definition, which is just a struct with a bunch of bools, one for each of the bits. And we can write a reset function, which takes a mutable reference to flags and sets everything to false. Now we can finally build a struct that represents the register file that I described earlier. We have BC, DE, HL, which are 16-bit registers. We have A, which is an 8-bit register. We have the stack pointer, which is a 16-bit register. And we have the flags. And the program counter we're going to deal with separately. At boot up, everything starts at 0. And finally, we can describe a bunch of getters and setters, both on specific registers and on arbitrary registers using our register kind enum that we made before. If RAM is only 8 kilobytes and VRAM is only 8 kilobytes, what do we do with the other 48K? Is that space wasted? Well, there's this thing called memory mapped I/O, and it's really cool. What is this memory mapped I/O thing? A processor is obviously connected to RAM. There are instructions that say load this thing from RAM or store it in RAM. When we have memory mapped I/O, instead of all the addresses going directly to RAM, the wires split off and do some other stuff. Maybe the addresses from C000 to DFFFF go to RAM, and maybe the address 0 up to 8000 does some other stuff. That other stuff could be, for example, if we load FFA3 into the address pointed to by the BC register, maybe that changes the sound mode on the Game Boy. Now that we understand that, we can dive into Game Boy's actual memory map. Remember, Game Boy has 2 bytes of addressable address space. There's roughly 65,000 values. We can divide this in half. We have 0 up to 7FFF and 8000 up to FFFF. We can divide that in half. And now we can start going over everything. At the very bottom, we have the restart and interrupt vectors, and this is also where the boot ROM goes, by the way. Then we have the cartridge header. The rest of the space, up until 3FFF inclusive, is bank 0 of cartridge ROM. From address 4000 to 7FFF is cartridge ROM again, but banks 1 through XX. There's this notion of banks that I'm just not going to talk about now, but we'll get into it later. Games like Tetris and Dr. Mario only use bank 0. So this is the cartridge section of the memory map. Then we have character RAM, BG map data 1, BG map data 2. This is video RAM. Then cartridge RAM until BFFF. Then we have the internal RAM, bank 0. The internal RAM, the other banks on a Game Boy Color. On a regular Game Boy, it's just more RAM. Then there's this section called Echo RAM, which is really weird. Anything you write to bank 0 of RAM just appears in Echo RAM, but you're not supposed to look at it. Then we have object attribute memory. This is also known as the sprite attribute table. Then we have unusable memory. Then there's a little bit of memory at the top that's super important. The last 256 bytes from FF00 up until FFFF. At the very bottom, we have I/O registers. SB, SC, DIV, TIMA, TMA, TAC, IF, etc. There's a lot of these. This is the first 128 bytes. Then the next 127 bytes is called the 0 page. This is super fast RAM. It's also known as the high RAM. And then the very last byte is the interrupt enable flag. Finally, we have enough context to understand the Rust code I wrote associated with the memory subsystem. Ignore all the warnings here. I recently set up the Rust language server properly, and Rust is detecting all of my code as dead code since it's not wired into the entry point yet. Memory struct contains all the memory that is actually addressable, in addition to instances that are needed to manage the special memory map sections. For now, the only extra thing is a PPU registers instance. We'll talk about that in a different episode though. Here we see main memory, video memory, and ROM bank 0 are declared as simple VEC-U8s. Addresses are new types around U16s. We have an enum for direction, either positive or negative, that we'll use later to describe the direction of offsets to addresses. We can create an address indirectly from the contents of one of the 16-bit registers, or directly from an arbitrary U16 value. The I/O memory offset frequently needs to be applied, so there's a shorthand for constructing this sort of address. We can offset an address by some U16 in some direction by creating a new address that wraps a U16 that has the offset applied. Note that we can use self.0 to refer to the type inside the new type wrapper. Maybe these should also be wrapping adds and subs to mimic the behavior of a real Game Boy though. We can also turn an address into a 16-bit register. Main memory is 0x2000 large, in other words 8 kilobytes, as is video memory. Bank 0 of ROM in a cartridge is 16 kilobytes. The main interface between the memory module and the rest of the system is the ability to load and store 8 or 16-bit values from or to some arbitrary address. This can be modeled as a big switch statement, most of which I have yet to implement. For all bits of memory that I don't expect the boot ROM to access, I am panicking in an attempt to catch bugs. You can probably see the PPU uses some of the I/O registers here. Main memory is between C000 and DFFF. To access, we can directly index into the main vector after subtracting an offset. We do the same sort of thing with video RAM, which we don't treat as the separate character RAM and BG map data just yet. Finally, ROM bank 0 is at the bottom. For now, we actually hardcode the boot ROM to the last 256 bytes, as this is where it lives when the Game Boy is first started up. To load 16-bit values, we can use a nice helper method to take 2 bytes and combine them together. This way, we can have a similar switch statement as above. At some point in the future, I'll figure out a nice way to refactor this bit of code to reuse the same control flow as the 8-bit loading section. Finally, we can store memory as well. That's it. Can you believe all that explanation in the beginning was needed for such a small amount of code? Today we talked about memory, how the Game Boy stores the boot ROM, how we discovered what the ROM did, how we can refer to binary streams in hexadecimal. We talked about the difference between ROM and RAM, and the differences between registers and main SRAM. We went over memory mapping and the Rust code that implements all these things. That's it. See you next time.